Number 14, we have a person sitting on a spinning stool, given its rotational speed at the beginning, given the mass moment of inertia of the system. Okay, then we are told that the person extends their arms. The extension of the arms actually will change the mass moment of inertia of the system. And we're given a final rotational speed. We want to determine the change in the energy of the system as they extend their arms and whether it's a gain or a loss. Okay, so if we think about this for a second, we're talking about energy, and we're also talking about angular momentum, because we know that with no external torques there has to be the same angular momentum initially and in the final state. Alright, so conservation of momentum will tell us, let us determine a mass moment of inertia of the final state, and then we can use that to determine an energy loss. So you have to really think through this problem and develop a plan of action. So let's do conservation of momentum. In angular terms, that says that mass moment of inertia times the initial angular momentum. Okay, we just have one thing rotating, or one system rotating, the person in the stool. Okay, and it's going to be the same after they extend their arms. So simple equation here. We're given I initially 0.8 kilogram meters squared. We're given the initial omega 0.6 radians per second. Okay, don't know a final I, we do know a final speed, 0.4 of a radian per second. Alright, so we can easily find I here. I won't even do that on a calculator. 0.8 times 0.6 divided by 0.4 will give us 1.2. The units will be kilograms meters squared. Okay, the radians per second on each side are consistent and cancel out. Alright, so let's look at conservation of energy. We'll have some initial kinetic energy. Okay, the extension of the arms, if we're looking at the person, the extension of the arms would actually be some energy added into the system, but we're going to consider that a really mechanical energy lost by the system. So I'm going to write it like this, because that's really the only way we can work this problem. Okay. Another way of thinking about that is the amount of energy lost is just the difference in the kinetic energies. So I start off with a bunch of kinetic energy. I have some kinetic energy at the end. The difference between those two would be any energy loss. If that turned out to be negative, I would actually have an energy gain here. Okay, but we'll work through and see what the numbers are. Let's calculate the initial kinetic energy. We're rotating, so that's 1/2 I omega squared. So that's 1/2 0.8 times R 0.6 squared. And that number again, I'll whoops, let's see. Okay, if you've been working along, hopefully you've seen a slight, not an error, but a mistake that it is an error. A mistake that I've made. I did not read the problem carefully. These are revolutions per second. Okay, up here at the top, it really didn't matter, okay, because whatever units I had are consistent and would cancel out. Down here, when I'm doing energy, I have to be really careful, okay, because energy would need to be in radians per second. The mega would need to be in radians per second in order for my energy to work out to be joules. Alright, so we've done this a lot in these types of problems, but let me write it out here a little more formally. It just takes us a minute. This was revolutions. Actually, let's do it this way. Omega 1 is 0.6 revolutions. So I'm going to convert up here just to make things a little more straightforward. This is revolutions per second. We have 2 pi radians per revolution. Okay, so that will give me, try to punch into the calculator. Which I don't have in a calculator, but I'll take the time to do it. Come on. 0.6 times 2 times pi. 3.77 radians per second. Okay, and I'll do the same thing for omega 2. Okay, 0.4 times 2 times pi should be 2/3 of that, or 2.5 radians per second. Alright, so need to be careful with units. I'll get this changed up here. So that has to be omega 2 radians per second, and this is 3.77. Okay, that number will be 3.77 squared times 0.8 divided by 2. Struggling with my calculator here. So I get 5.685. And when we check our units, we'll see kilograms, meters squared, seconds squared. Radians are unitless. That's a Newton meter or a joule. Okay. Same thing quickly for number 2. 1/2 I omega 2 squared, or our final one. It's 1/2. We used our I up here, 1.2. So extending the arms increases the moment of inertia. That makes sense. Okay, and 2.5. And that will give me 0.5 times 1.2 times 2.5 squared. 3.75 joules. Okay, looks like I have a little bit of round off error there. That should have been 2.51. And this gives me I'm taking my time on this because you on a test would also have to take your time, and I want to have a good feel for the total time that takes to work these problems. Especially when you get in a hurry. 3.78 is what I get there. Okay, so my energy loss is my initial 5.685 minus 3.78. Okay, 5.685 minus 3.78. It's positive, so it is an energy loss because that's what I assumed it to be. And that gives me 1.9 joules loss here. Okay, reading the problem, it did ask me to state that. Okay, that was a fairly involved problem, not in calculations, but just in keeping everything straight. Using conservation of momentum, angular momentum, to determine my final mass moment of inertia. Then using conservation of energy to compare the final and initial kinetic energies to come up with energy loss, making sure my units were correct. And just to make things consistent, I will write this as revolutions. Again, they cancel out. So as long as I was consistent, those units did not matter in that part of the problem. We'll finish off there.